Lesson 5. We're going to talk a little bit more about lines and planes. Now, the nice thing is, these are kind of easy ideas again, but it's simply one of those things you need to identify. And as always, make sure that you put these postulates and theorems into your little books. You'll need them later. So, new concept. Now, I would almost bet that every one of you knows what these symbols are. What's that symbol mean? Upside down T, that means perpendicular. You guys. Oh, well, do you know it now? Okay. So now when you see that little upside down T, that means that things are perpendicular. Okay. Okay. Hopefully, you actually know what this one is. Okay, I gotta make this a little smaller. Okay. So, parallel, right? Okay, that one we've got. Not a problem. And of course, you know that little box in there means that it's 90 degrees. And you know that this little arrow here and this little arrow here means that things are this here and this here. The same, okay? Same meaning what, though? The same what? Collinear. I mean, they are coplanar, yes, but that's not what it means. What, okay, if you've got a square sitting here, what would X, W, and Y, Z, what would they be to each other? They'd be parallel, so that these marks here mean that these two are parallel, okay? This here, since it's a different set that's parallel, they got two little marks on them like that, identifying parallel, okay? Now, we also have a word that if they don't intersect and they're not in the same plane, we call them skew lines. Basically what that means is if I would have, if both of these are laying on my podium, they'd be laying here like this, right? But if I've got one going up over here and I've got one holding here, are they going to intersect? No, they wouldn't intersect, so these are classified as skew. Okay? Skew, yes. Skew. Skew. Got it? Skew. Okay. So, theorem 1. Now I'm going to go through these theorems and postulates and I'm going to talk about them so you get a little bit better idea. Again, like I said, make sure you put them into your little books. If two parallel planes are cut by a third plane, then the lines of intersection are parallel. Now, if I'm talking about the room, is the ceiling and the floor, are they parallel planes? Okay. Is the front wall another plane? Okay. So I got two parallel planes, ceiling and floor, cut by a third plane, the front wall. Are these lines parallel? So is the line that's up there at the top parallel to the line that's down here? Would have to be, right? I mean, as far as I know, this line that's up here, part of that ceiling up here, would have to be parallel to this line down here, right? Okay. Make sense? Sort of, kind of? Maybe? Okay. Well, let's try it this way. Is that wall over there parallel to this wall here? Okay. I've got a metal line that goes all the way down this way, right? Do I have another one on the other side? Okay. Are both of those lines on the ceiling? This strip here and the metal strip that's over there, are they on the ceiling? Are they parallel? Yeah, because they're going in the same direction, correct? And we know that because of the way a box is set up or a room is set up like this, opposite sides are supposed to be parallel. So that means that those lines would be parallel. It's always kind of hard to visualize these things. That's why I kind of put things in terms of a box or a room. So, if I am looking at this, okay, there's a lot of stuff there, right? But I've got plane S and I got plane T. I got this lighter blue cut through here, right? Now, since these planes are supposed to be parallel, lines EF and GH are parallel. This plane slices through here, so I got CD and AB. They're parallel. As time goes on, you'll be able to look at it and you'll be able to see them a lot quicker. Okay. Now, here's a theorem that goes along with this stuff. If two lines in a plane are perpendicular to the same line, then they are parallel to each other. So if I look at the ceiling and I got those steel bars going across, is this line here parallel to this line over here? Okay. Is the line that comes through here perpendicular here? Okay. Is it perpendicular over here? Yeah, because these are all square triangles, right? They got to be perpendicular. So, if they're perpendicular to the same line, then they're parallel to each other. So this is perpendicular to that, therefore they have to be parallel. No. This only works when we're talking about perpendicular and parallel. And perpendicular and parallel usually goes along with squares and rectangles, right? Triangles is a whole other story that we'll be talking about later. Okay? Now, in a plane, okay, so I got my ceiling again, it's a plane. If a line is perpendicular to one of two parallel lines, then it's perpendicular to the other one. So again, if I'm looking at what I've got up here, I've got this line that's running right here. It's perpendicular over here, correct? Okay. And perpendicular over here, right? This line is parallel to that one. So when we're looking at this, we've got to be able to see what is parallel, what is perpendicular, and understand that once I know certain things, I've got it. If I know that something is parallel and I got a perpendicular line going through it, I know it's perpendicular to the other one. Okay? So, if I look at this one down here, this says that P is parallel to Q, correct? So, I got line R going through here, right? Is this right angle here? Is it perpendicular? So if these two are parallel, that's 90 degrees. Does this have to be 90 degrees up here? Are you sure? Positive? Stake your life on it? Good. I would stake my life on it because it has to be. That's the way the rules go. Now, the next three theorems kind of go together. If two lines are perpendicular, then they form congruent adjacent angles. If you look at the ceiling, we've got steel track that goes across. We got steel tracks that go down, right? Are all of these tiles the same? Are all of these tiles square? Do all squares have 90 degrees? Now, if this rule did not work, we couldn't make a ceiling like this. Okay? If two lines form congruent adjacent angles, then they're perpendicular. So if I make sure that all of these tiles are square, okay, that they're 90 degrees, then I don't have to worry about them. I know that I can put them into perpendicular grids like this, right? As long as I got the right sizes on there, I can just drop them right in. Okay. Is the last one down there kind of like, well, duh, right? But again, when it comes to math, we need to be able to state things so that when we are talking about whatever, we can go and say, hey, this is the reason why, because of this. This is the reason why, because of this. So, if I know that I got right angles, I know they're all congruent. Why? Theorem 5-6. The way it works. So, if I go and take a look at this here, looks like a whole lot of stuff, doesn't it? Okay? So, question comes down, oops, I got a picture, there we go. So I am told that AB is parallel to DC. I am told that KL is perpendicular to DC. I am told that PQ is perpendicular to DC. So what's the relationship between KL and AB? So KL and AB, what would they have to be? They would have to be perpendicular, right? Because this is perpendicular to that, this is perpendicular to that. We were told that this is parallel to that, therefore, perpendicular, perpendicular. It's not all that bad, it's just really going through and decoding what it all has there for us. So, let's try this one. Through a point not on a line, there exists exactly one line through the point that is parallel to the line. Did you get that? A riddle? You like riddles, huh? Okay. Oh, riddles are fun. Except in math, we don't have any riddles. We have facts. That's all we have. So, I'm going to make a line. So there's a line, and there's my point. Okay? So, do you agree that if I go and use the function of copy and paste on a computer, that these are congruent, they're parallel, they're identical? You agree with me? Okay. So, I can only get one line through this point. Okay? Now, theoretically, I can put an infinite number of lines through any point, correct? But how many of them will be parallel to this one? Only one. Because everything else would be a little bit different angle, right? So that is what is being said here, through a point not on a line. Okay? There is exactly one line through the point that is parallel to it. So when I look at this one down here, I got line DE. Point K, there is only one line that goes through it that can be parallel to DE. Okay. Transitive property. We talked about that before. You know, if one goes to 2 and 2 goes to 3, does 1 go to 3? Yep. So, remember what we talked about. If I go and say that this yardstick here is the same as this yardstick here, and I say that this yardstick here is the same as this yardstick here, does that mean that this yardstick here is the same as this one here? Would it have to be? Yeah. I mean, it's that whole idea that you can buy a pack of AA batteries and it doesn't matter what order you put them into the calculators, right? If it needs 4 batteries, you can put them in any order. They are all the same. 1 is the same as 2, 2 is the same as 3, 1 is the same as 3. Yeah, but you get the idea. Yeah, you just keep adding on. No, that's not a problem. So, here we go. A little practice here. So, if I have A there, and I said if the horizontal planes are parallel, identify lines that are parallel. So, let's see. We got to make sure that I go down to 14. Got to make sure that we get everybody in there. Wouldn't want to leave anybody short. Oops, wrong one. Okay. No, we don't have 124. 1. So, number 14. Not here. How do you like that? Number 12. Cameron. So, Cameron, if the horizontal planes here are parallel, so that means that this plane here is parallel to this plane down here. Which lines are parallel? Well, what lines do you see, sir? AB. So is AB parallel to anything? Do you say CD? You got to take your hand away from your mouth so I can hear what you're saying, sir. So AB is parallel to which line? FE, yes, that's absolutely correct. What about CD? Is it parallel? Well, these lines are parallel, correct? So that'd be like my ceiling and my floor, correct? If I had a wall that went up here at an angle up front here, this line here would have to be parallel to that line up there. And since AB is parallel to CD because they're on the same plane, and CD is parallel to EF because these planes are parallel and it's the same plane. So the only way that we know that this one is parallel to this one is because AB goes to CD, CD goes to EF. Transitivity problem. Okay, doke. Let's move on to B. So, number 9. Not here. Terrible. 13. Serena. Okay. In this figure, I have CD parallel to GH. Okay. I have CD perpendicular to AB. What should be the relationship between AB and GF? Absolutely correct. Because these two lines are parallel, this was perpendicular up here, this has to be perpendicular down there because they are parallel lines. Okay? So, moving along, C. Okay? 2. 12. Well, we already picked on camp. 1. Parallel? You didn't give me a chance to read it yet. So you got RS is perpendicular to XY, and I have VW perpendicular to XY. RS and VW have to be parallel, and you are absolutely correct. Okay. Wow, getting ahead of me here. Be careful about this. I'll give you guys some harder work to do. 4, Tristan. Huh? Question. What is the relationship among the angles at the points of intersection of RS and TU and VW with line XY? What are they? They're all right angles, so they're all right angles, so they must be what? They must be 90 degrees, so they're all right angles. They're all 90 degrees. So that means that they are all, well, lines are perpendicular. Yes, they are the same. But what is the word that we use for the same when we're talking shapes? Congruent. Yes. There we go. Now we got it. So they're all congruent. Good. All right. Moving on here. E. Let's see. 2. Oh, that's right. We're 6. There we go. Storm. If line XY goes through point M, so I got line XY going through point M, and XY is parallel to CD, how do I know that JK is not parallel to CD? I know that line XY goes through point M. I know that XY and CD are parallel. How do I know that JK is not parallel to CD? Huh? Looks don't cut it. There has to be a rule. There has to be a reason. Ooh. Okay, what's never mind? Never mind. Okay, so you're phoning a friend, so you're going to go with Cameron. Yeah, it does. We see that right here. What's the deal? Why isn't this parallel to this down here? Remember I said those postulates and theorems, we got to have a reason. Yes, ma'am. Okay, two different lines, parallel, okay? There's only one parallel line that goes through a point that's not on the line, right? Yeah, that's it, okay? They're skew? No, they'd be skew lines if they're on the same plane, so they're not skew, they intersect, okay? Careful. Okay, so F says Carlotta is assembling the floorboards for her deck. How can she be sure that all of the boards are parallel to one another? So number 10, that puts us at Isaac, who is not here. That puts us to 3, which is Parker. So Parker, how would I know that if I put the floorboards down that they're all going to be parallel? Okay, I line them up side by side. That's one way of doing it. But I want a mathematical way of doing it. Have you ever seen, okay, let me put it this way. Have you ever seen floorboards on a deck? Okay. Do you know what a joist is? The joists are the big beams that run on the underside of it that hold up the floorboards. What are the floorboards always to those joists? Okay, so if I make sure that all of the boards are perpendicular to the joist, would they be all parallel then? Are you sure? Stake your life on it? Oh, excellent. Yeah. All right, so now you've got the assignment here, so you can start working on that.